Now our next speaker is Professor Kavita Jain from JNCASR. She will be talking about slow quench dynamics in classical systems. Yes.
Okay. So first of all, I would like to wish Ustansi and Deepak a very happy 70th birthday. So your influence, your impact of your work is very clear in the list of speakers and participants in this meeting. And thank you so much for your guidance and mentorship through all these years. And I really hope and wish that you have many, many happy, healthy, and productive years ahead. Okay, so I will speak about one problem, a small problem that I have been interested in for a while. So this work is done with a former PhD student, Priyanka, and former postdoc, Sadhu. So before I tell you what I'm interested in, okay. What I'm interested in, something I'll tell you, which you already heard in Musansi's talk, but let me just repeat anyway. So this is the standard problem of phase ordering. So what one is thinking of here is a classical system which exhibits a second order phase transition. And we start with this system, let's say it's a thermal phase transition. So we start with the system in the disordered state, that means above TC. And then the temperature is cooled instantly, so that to TC or below TC. So then here is the simulation from a 2D Ising model. So when we just quench it, then the system is in disordered state, and there are these positive and negative spins denoted by this black and white patches. And these are the domain length. And as time goes on, the domain length grows with time. And this length grows in time with this exponent 1 by Z coarsening. So this is what you already heard. So today what I'm interested in is asking questions about slow quench. So what does that mean? So again, I'm thinking of, again, the same sort of system. Again, it's prepared in the disordered state, but now we quench it in a finite time, tau. So we're quenching it in a slowly. And then once you have quenched, once you have reached your final temperature, just stop your simulation or experiment and then look at its properties. So that's the question. Okay, so that's the situation that we are thinking of. So clearly when tau is very small, system is very close to the disordered state and it will have lots of defects. As tau increases, the number of defects will reduce. So therefore one is interested in asking, how does the defect density change with tau? In particular, we know that there will be more defects compared to the equilibrium state. So precise question is, how does the excess defect density, that means this difference, change with tau? Typically it goes as a power law, and one is interested in understanding what this exponent is. So there's a very standard argument to understand this exponent, which goes by the Kibble-Zurek argument. And for concreteness, I'm going to assume all through that we are going to quench the system to the critical point. So the argument says the following, that there are two time scales in this system. One is the relaxation time, and the other is this quench time tau. So suppose we are away from the critical point, then the system is in this disordered state where, because the temperature is still changing, it is slightly away from its true equilibrium state, but the relaxation time is of order 1. But the time that is left for it, remaining time till we stop our simulation, is of order tau. So therefore system is able to relax and the system basically is in equilibrium. But when we are close to the critical point, then because of critical slowing down, the relaxation time diverges with the coarsening, with the correlation length, with an exponent ZSS, that is the dynamic exponent in the stationary state. So when they're close to the stationary state, the time left may be much smaller than the relaxation time. And in that case, system is not able to relax and it's not in equilibrium anymore. So there are these two regimes. There's a time scale, Kibble-Zurek time scale, below which the system is in equilibrium and above which it's not in equilibrium. So what is this time scale? That's basically what I just said. That is, one can basically estimate it by saying that the remaining time, when if it's all the order of the equilibration time. So when these two time scales are matched, that will give you how this Kibble-Zurek time scale scales with for example, the quench time. Okay, so this is the sea of exponents that you get over here. So it's a simple exercise that one can work out. Okay, so however, the question was about residual defect density. So furthermore, the argument is the following, that when beyond this Kibble-Zurek time scale, there's no further evolution of the system. The dynamics are assumed to be frozen. So which means is that whatever defects are present at the Kibble-Zurek time scale, the same ones are there, the same thing is inherited and they're passed on till our final quench time. So then if excess defect density, just by units of density, so therefore just by dimensional analysis is psi to the power minus d, psi being the correlation length again, and we can write psi in terms of the Kibble-Zurek time scales, and therefore that gives you this power law. Okay, so that was the original question, that is how does residual defect density scale with tau? And this scaling has been verified numerically, experimentally, and so on. So this has been questioned recently. And the question is that, of course, the dynamics will not be frozen. It's not like spins are just sitting around. They'll be doing something. And the proposal of Biroli et al. Is that why don't we model this non-equilibrium regime as though it's an instantaneous quench from Kibble-Zurek time scale, or from Kibble-Zurek temperature to the final temperature. And therefore, actually, coarsening occurs during this, in this regime. So when you invoke coarsening, the fundamental difference that happens from the Kibble-Zurek argument is that this length scale is not the equilibrium correlation length, rather the coarsening length, which has a different exponent, Z coarsening in general. And therefore, if you just work out the same calculation, the excess defect density now decays with the quench time in this manner. So there is this ratio of the stationary state dynamic exponent and the coarsening exponent. So again, this scaling has also been verified numerically in the systems where these two exponents are different. Of course, if these are equal, these two theories will coincide. Okay, so we had just very small question. We just wanted to understand, we just wanted to test, in fact, this coarsening proposal in the framework of a solvable model, because everything else has been numerical and it's nice if it can actually work out things. So we just worked with the simplest, perhaps the model that you can imagine, which is simply the Glauber Ising chain. So as you know, so this is just a one-dimensional Ising chain, and the dynamics are through single spin flips. And the master equation was the standard master equation, where the rates are the Glauber rates, in which the temperature enters in this manner, tan hyperbolic 2 by t. Okay, and because we are saying the temperature is changing with time, we have to choose a cooling protocol. So we quench the system from infinite temperature to zero temperature in a finite time tau according to this protocol. So it's like 1 by logarithmic, and there is this factor in front, this number alpha. Small alpha means that the finite time quench is slow, and large alpha means that the finite time quench is fast. Okay, so fine. So we just put all this together. That means we just go back here and to a master equation, use this cooling protocol, and write down the equation for the 2-point correlation function, the equal time correlation function. So if the temperature was constant, this is something all of us have written down in school. This is a standard equation, okay? But now the difference is that these coefficients also depend on time. This problem is it's nice that this problem is solvable, and this is known for a long time. So the idea is simply that basically you can diagonalize this space part by going to these eigenfunctions. So if you can expand your correlation function as a linear combination of these eigenfunctions, which obey this, which basically is the right hand side, so then one can work it out. So precisely this problem was actually was visited a few years ago. However, approximate solutions only were obtained, and very recently, very detailed simulations were done. So our contribution is simply to analyze this double integral in detail. Okay, so what do we find? So we again looked at this the defect density and see it should decay as a power law as expected. However, this power law is same. The prediction coincides with the Kibble-Zurek answer as well as Biroli et al. Simply because it happens that these two exponents are equal for this model. Both are equal to 2. So that's kind of unfortunate, but I mean, that's what it is. Okay, so therefore our test is not yet done. And therefore we looked at something else, that is what happens not at the end of the quench, but slightly away from the critical point. So the idea therefore is that if we model the non-equilibrium regime by the instantaneous quench from the Kibble-Zurek temperature to zero temperature, then if we know the correlation function for small distances should behave like this. So this is the equilibrium value, this is linear because of the Porod's law, and this is because of our coarsening exponent half. okay, 2, right? And therefore, from this, it follows that the difference in the correlation function should scale linearly with the time difference. Okay, so this will be the prediction if we model the non-equilibrium regime by the instantaneous quench model, and therefore we can ask if we can test this prediction. Okay, so this is what we worked out from this double integral, and we find that indeed the linear scaling holds, provided this number alpha is larger than half, otherwise it's sublinear. What that means is that we can model, this suggests at least, that we can model the non-equilibrium regime in slow quench problems by the instantaneous quench dynamics, provided the finite time quench is fast enough. If it is too slow, then it's something else, it's some other dynamics.
Professor Jain, you have 2 more minutes.
Yeah, thank you. Okay, so just to be sure that it's not some one-off answer, one-off thing, we also studied a mean field zero range process. And Mr. Ansel has already told you in the morning that it has a condensation transition, a non-trivial critical point, but unfortunately, these 2 experiments happen to be equal in this model as well. But we looked at an analogous quantity here in this zero range process as well. And again, Priyanka's simulations showed that for when this our slow quench is fast enough, then the behavior is like the instantaneous quench model. But if the slow quench is slow enough, then it's not. Okay, so that's our sort of key result. So this is what is summarized here, that we know that we have a non-equilibrium regime beyond a certain scale. And the idea is that can we consider it as though it's can we describe it by the usual coarsening problem? And our answer is that yes, provided your slow quench is fast enough. There are things which we still don't have a complete understanding of. For example, if you ask me, can I give a simple argument to understand what this slow, where we have sublinear scaling? I don't have a simple argument to understand. And so that's something I think I'm missing, and I would like to understand it better. There are lots of problems that we would like to understand and extend this further. We would like to understand, we would like to also study other models where these 2 experiments are unequal. Most of the studies are on equilibrium models, and we would like to understand, extend these studies to non-equilibrium. And I'm aware of only one study, which is from our study. And basically, non-equilibrium models with slow quench are just not studied. I mean, I don't know of any other study. Of course, you can run this slow quench stuff with any model with 2-second order phase transition. And however, it would be nice to find tractable models. So again, this Ising chain is the only model which I know for which some analytical work is doable. So again, it would be nice to have some more such models. So with that, I will stop. Thank you.
Thank you, Professor Jain. Questions? There is one question in the chat box from Soham Biswas. How do you do the finite time quenching in the simulation by gradually decreasing the temperature?
Yes, that's right. So we just gradually change the temperature in finite, so I showed you this protocol. So we just change the temperature in this manner. So temperature is changing with time. Yes.
So I had a question.
Yes.
So what you call slow and fast depends on the protocol for slowing down. Is this sort of a clear what would be if you had some other protocol for
Yeah. So right. So we just studied other protocols also. So the thing is that this temperature protocol looks a little weird. But remember, what enters the master equation, etc., is tan hyperbolic. So basically, what is entering the master equation is the power law in tau minus t. Okay. So therefore, if you take some other protocols which are faster than this, you basically go to instantaneous quench problem. So you can do a finite quench, but if it's faster than these power laws, then you will go to the instantaneous quench problem.
Okay, thank you.
There is another question in the chat box. So quenching to 0 temperature, the system will never freeze in any metastable state?
Not in this model. Suppose if I have a disorder, then I can expect, but not in this model, no.
So I have a question.
Yeah.
Which is so basically, if you quench slow enough, then you're saying you can't model it as an instantaneous quench, right?
Yeah, so slow enough means that this exponent alpha is less
Yes.
than 1/2. Yes. So we have a different answer, but I mean, I would like a simple understanding of it, which I'm still missing. We tried a while to understand what is causing that, but I don't have that understanding. That is, what are those dynamics which are giving me a nonlinear, a sublinear dependence? So that understanding I don't have. Otherwise, it's basically up to some prefactors, the scaling is same as the instantaneous quench problem.
So, but if you have a non-instantaneous quench, can you treat it within the mean field, maybe? Where you're like forcing the system slowly or something?
I don't know what by mean field. At least, I mean, this.
I mean, just not the complicated model, but like, let's say I'm doing a slow quench on a mean field model or something.
Yeah, I don't know. I mean, most likely exponents would change. Many times
Yeah.
it happens. So then it would not be a test of the proposal. So I would like those exponents to be exactly correct.
I see. Okay.
Yeah.
Thank you.
Any more questions? If not, then let us thank Professor Kavita Jain again.
Thank you very much.